Quasi-hereditary algebras, lecture 13, the RIngel dual. Let us start with the setup. Let K be an algebraically closed field and A a finite-dimensional K algebra. Let L1, L2, and so on Lk be the complete and irredundant set of representatives of isomorphism classes of simple A modules with a fixed, chosen, linear order on them. We assume that our algebra A is quasi-hereditary for this order. In particular, for each I, we have the corresponding standard module delta I defined as the quotient of the indecomposable projective cover Pi of Li by the trace in Pi of the projective modules Pi plus 1, Pi plus 2, and so on, all the way up to Pk. Also, for every I, we have the corresponding costandard module nabla I, which is defined as the intersection of the kernels of all homomorphism from the injective envelope II of Li, the indecomposable injective envelope, to the indecomposable injective modules II plus 1, II plus 2, and so on, all the way up to Ik. Then we have the category F delta, which is the category of all A modules, finite-dimensional A modules, which have a filtration with standard subquotients, the so-called standard filtration. And we also have the category F nabla, which is the category of all finite-dimensional A modules, which have a filtration with costandard subquotients, the so-called costandard filtration. On the last lecture, we defined tilting A modules as objects in the intersection of F delta and F nabla. Moreover, we proved the following classification theorem due to RIngel. Claim 1. For each I between 1 and k, there is a unique indecomposable tilting module Ti, such that delta I is a submodule of Ti, and the cokernel of this inclusion has a standard filtration. Furthermore, if delta J appears with a non-zero multiplicity in a standard filtration of some Ti, this implies that J is less than or equal to I, and moreover, the multiplicity of delta I in Ti equals 1. And finally, any indecomposable tilting A module is isomorphic to Ti for some I. This means that we have exactly k isomorphism classes of indecomposable tilting A modules, and so we have defined the characteristic tilting module for the algebra A as a direct sum of the representatives of these isomorphism classes. So our characteristic tilting module T is defined as a direct sum of all Ti, where I ranges from 1 to k. Next, we define the main protagonist of the present lecture, and that's the RIngel dual of A. So the RIngel dual of A is defined as the opposite of the endomorphism algebra over A of the characteristic tilting module T. And the RIngel dual is usually denoted by R of A. Note that by definition, the algebra R of A is basic. That's because it's the endomorphism algebra of a multiplicity-free direct sum of certain indecomposable modules. Here is an example. Assume that the algebra A is directed in the sense that all standard modules are projective. Then all costandard A modules are simple, and therefore the tilting A modules are exactly the projective modules. So the modules which have both a filtration with projective subquotients and with simple subquotients are exactly the projective modules. So this means that our characteristic tilting module T is just a basic projective generator of A mod. Consequently, the RIngel dual R of A is a basic algebra that is Morita equivalent to A. So in particular, if A itself is basic, then A is isomorphic to R of A in this case. Next, we define the so-called RIngel duality functor. So we have the functor f from A mod to R of A mod, which is defined as taking a homomorphism from the characteristic tilting module T to blank. So that's the obvious functor from A mod to R of A mod. It follows directly from the definition that this functor sends the indecomposable module Ti to the indecomposable projective module Pi over the algebra R of A. In particular, we have that the indecomposable projective R of A modules are indexed by the same set, by the set 1, 2, 3, and so on up to k. And in particular, it follows that the simple R of A modules are also indexed by the same set. So we started with defining the natural order 1, 2, 3, and so on up to k, and the natural order is the order being less or equal to, which we used to define the quasi-hereditary structure on the algebra A. We also have the opposite order, 2 less than or equal to, that's of course the order of being greater than or equal to, on the same set 1, 2, and so on up to k. So we have two natural linear orders on this set, being less than and being greater than. So in other words, our choice of an order on A simples induces two natural choices of an order on the simple modules for the RIngel dual R of A. Now we can formulate the main result. That's a theorem which is due to RIngel from the same paper which was the main paper on which the previous lecture was based. Claim 1, the pair R of A and the opposite of the natural order on 1, 2, and so on up to k is a quasi-hereditary algebra. And the second claim, the second RIngel dual R of A is Morita equivalent to A. A couple of remarks. In particular, if A is a basic algebra, then the theorem claims that the second RIngel dual is isomorphic to A. Another remark, if we take the second RIngel dual, then according to claim 1, we should take twice the opposite of the natural order, so the order on the R of A simples, with respect to which it's a quasi-hereditary algebra, is the same as the order on A. So the second RIngel dual is Morita equivalent to A, and we have the same order on simple modules as on the original algebra A. And the final remark is that claim 2 explains the wording dual in the terminology. So if we take the second dual, we come back to the algebra A, of course up to Morita equivalence. In order to prove the main theorem, we first have to discuss standard R of A modules. So what we will show is that our functor f maps the costandard A modules nabla I to the standard R of A modules with respect to the opposite of the original order. Let us take some short exact sequence in F nabla. So X is a submodule of Y, and the cokernel is Z, and all X, Y, and Z, all these three modules are in F nabla. Since F is defined as taking Homs from the tilting modules, and the tilting module has a delta filtration, and X has a nabla filtration, the first X from T to X vanishes, so applying our functor f to the short exact sequence results in a short exact sequence. And this is true for any original short exact sequence in F nabla. So here is a short exact sequence in F nabla. Nabla I is a quotient of Ti, and the kernel has a nabla filtration. So if we apply f to this short exact sequence, we will get that f of nabla I is a quotient of f of Ti, and this is exactly the projective module Pi over R of A. Moreover, f of the corresponding kernel has a filtration with subquotients f of nabla j, where j is strictly smaller than I. And as each of these f of nabla j's is a quotient of the corresponding Pj, the indecomposable projective over R of I, it follows that delta I R of A is a quotient of f of nabla I. And in order to prove that these two modules are isomorphic, we just need to prove that for any j smaller than I, the multiplicity of the R of A module Lj in the indecomposable projective R of A module Pi is the same as the multiplicity of this simple in f of ker I. But this is equivalent to saying that the Hom over A from Tj to Ti is isomorphic to Hom over A from Tj to ker I. If j is strictly smaller than I, then Hom over j from Tj to nabla I is 0, and this is because delta I doesn't appear in a standard filtration of Tj. So the only deltas which appear in the standard filtration of Tj are those which are indexed by the elements which are less than or equal to j, while I is greater than j. And therefore, if we apply Hom over A Tj blank to our short exact sequence, here the rightmost term vanishes, and so we have an isomorphism between Hom Tj ker I and Hom Tj Ti. And that's exactly what we wanted to prove. This gives us exactly this equality between the multiplicities of Lj in Pi and in f of the kernel. And this proves that f sends nabla j to delta I. So nabla j, that's a costandard A module, and delta I is a standard R of A module. Now we can prove the first claim of the main theorem. We already know that f sends costandard A modules to standard R of A modules. Moreover, we know that the kernel of the surjection from the indecomposable projective Pi over R of A onto the standard module delta I over R of A has a filtration with subquotients delta j, where j is strictly smaller than I. So if we look at the definition of a highest weight category, in order to prove claim 1 of the main theorem, it is enough to show that the multiplicity of Li, and this is a simple R of A module, in the standard R of A module delta I is equal to 1. The multiplicity of a simple in a standard module is a dimension of the Hom from the indecomposable projective to that module. And that's equivalent to saying that the dimension of the Hom over A from the tilting module Ti to nabla I is 1. And this is equivalent to saying that delta I has multiplicity 1 in Ti. But we know that this is true from the previous lecture, so this completes the proof of claim 1 of main theorem. In order to prove the second claim of the main theorem, we will need the following proposition, which is interesting in its own right. The claim: the functor f induces an equivalence between the category f nabla for A and the category f delta for R of A. This equivalence preserves first extensions, and the inverse equivalence is given by the functor g, which is defined as tensoring over R of A with the module T. Proof: we already know that f sends f nabla of A to f delta for R of A. And we also know that the functor f is exact on f nabla of A. Directly from the definition, it is clear that G is the left adjoint of f. This gives us the following adjunction morphisms. We have the counit epsilon of the adjunction from G after f to the identity, and the unit eta of the adjunction from the identity to f after G. So in particular, for a module M in f nabla of A, epsilon evaluated at M is a morphism from T tensor R of A Hom over RT, M to M, and eta is a morphism from N to Hom over A T, T tensor over R of A N. So here N is a module in F delta for R of A. If we take as M the characteristic tilting module T, then the first adjunction morphism is obviously an isomorphism, because here we have Hom over A TT, which is R of A, so we can move it through the tensor product to get T, which is M. So the first adjunction morphism is an isomorphism if M is equal to T. By the additivity of everything involved, the first adjunction morphism is an isomorphism for any M in the additive closure of T. So now, given any module M with a costandard filtration over A, We can write M as a quotient of some tilting module. The kernel will have a costandard filtration, which we can write as a quotient of some other tilting module, and so on. So we actually can write a finite resolution by tilting modules for any A module M with a costandard filtration. But we will only need the first two steps of this resolution. So we take this exact sequence and note that F is exact on F nabla and G is right exact. So G after F applied to this sequence will be an exact sequence, which we can now consider as a row in the following commutative diagram. So we have the identity applied to this sequence and G after F applied to this sequence, and the two rows are connected by our counit epsilon of the adjunction, and both rows are exact. So we have such a diagram, and in this diagram the counit epsilon evaluated to both Q prime and Q is an isomorphism. This is because Q and Q prime are tilting modules, and the counit of the adjunction is an isomorphism for all tilting modules. But now from the 5 lemma, it follows that the evaluation of epsilon at M is also an isomorphism, which actually shows that epsilon is indeed an isomorphism. In particular, G after F is isomorphic to the identity functor on the category F nabla for A. Next we claim that the functor G sends the standard module delta I over R of A to the costandard module nabla I over A. So the functor G undoes what the functor F does. Indeed, we know that delta I over R of A is the image of nabla I over A under F, and so G applied to F of something is isomorphic to something. This was proved on the previous slide. And similarly, G sends the indecomposable projective R of A module Pi to the indecomposable tilting module Ti over A. And we will later show that G is exact on the category of all R of A modules with a standard filtration. The bounded homotopy categories over the additive closure of T and over the category of projective R of A modules are equivalent by construction, because we have the functor F, which sends add T to RA projective modules and which is an equivalence by construction. Since the module T is self-orthogonal, so T is a tilting module and all x of positive degree from T to T vanish. So since the module T is self-orthogonal, the canonical functor from the bounded homotopy category over add T to the bounded homotopy category over A is full and faithful. For this claim, please take a look at lemma 2.1 in Happel's book about triangulated categories in the representation theory of finite-dimensional algebras. Now, for each I, we have a tilting resolution of the costandard A module nabla I. So it's a finite resolution of nabla I by tilting modules. Applying the functor F, which is exact on the category of A modules with costandard filtration, we will get a projective resolution of delta I. And the results on the previous slide imply that our functor F induces an isomorphism between the first extension space over A from nabla I to nabla J and the first extension space over R of A from delta I to delta J. And from this, using induction on the length of costandard filtration, one shows that F induces an isomorphism between the first extension space over A from nabla I to any module X with costandard filtration, and the first extension space over the RIngel dual from delta I to F of X. This implies that any R of A module with a standard filtration is in the image of the functor F, because we can successively build any such module by extending first standard modules, then extending a standard module with a standard length 2, and so on. And comparing with this claim on the previous slide, we see that all this belongs to the image of the functor F, because all this is built using the first extension, And the functor f provides an isomorphism between the first extension space over A for modules with costandard filtration and their images under F. In other words, the restriction of our functor f to the domain given by all A modules with a costandard filtration and the codomain given by all R of A modules with standard filtration. So this restriction is full, and that follows from the mentioned lemma in Happel's book. It's also faithful by the same lemma, and now it's dense, which we just proved. So this restriction of f is an equivalence which preserves first extensions, and this follows from this lemma in Happel, and the inverse is of course the adjoint functor g. And as a bonus, we have the g sends the category of all R of A modules having standard filtration to the category of all A modules having costandard filtration, and since it undoes the exact functor f, the functor g is exact on f delta R of A. And this completes the proof of the proposition. Now we can prove claim 2 of the main theorem. We start by noting that tilting R of A modules are exactly the objects in the category of R of A modules with standard filtration, for which the first extension from any standard module vanishes. Now we can pull all this back via the equivalence f, and we get the objects in the category of A modules with a costandard filtration, for which the first ext from any costandard A module vanishes. And this describes exactly the injective A modules, and these injectives indeed belong to F nabla. So let I be a basic injective cogenerator of A mod, then the above means that if we take the second RIngel dual of A, we will get the opposite of the endomorphism algebra of I over A. And this is clearly Morita equivalent to A. So let us consider one example. Consider the path algebra A of the following quiver. We have three vertices 1, 2, and 3, an arrow from 1 to 2, and an arrow from 3 to 2. So this algebra A is hereditary and hence quasi-hereditary. So this algebra has 6 indecomposable modules. The simple module L1, which is concentrated at the vertex 1, it also coincides with the injective envelope I1. It is also the standard module delta 1, the costandard module nabla 1, and the tilting module T1. Then we have the simple module L2 concentrated at the vertex 2, which coincides with its projective cover and with the standard module delta 2. We have the simple module L3, which is concentrated at the vertex 3, which coincides with I3 and with nabla 3. Then we have the projective module P1, which is concentrated at the vertices 1 and 2, with the identity map between them. It coincides with nabla 2 and with T2. We have the projective module P3, which is concentrated at the vertices 2 and 3, with the identity map between them, and it coincides with delta 3. And finally, we have the indecomposable injective module I2, which coincides with the tilting module T3. So the RIngel dual of A, by definition, is the opposite of the endomorphism algebra of the modules T1, T2, and T3. So T1 is L1, T2 is the module which is concentrated at the vertices 1 and 2, and T3 is a three-dimensional indecomposable module. If you look at the endomorphism algebra of this module, we see a surjection alpha from T2 onto T1, so we can kill this vertex and go from T2 to T1. We can embed T2 into T3, we call this beta, and we can actually project T3 onto T1 by killing the vertices 2 and 3 in T3. Note that alpha is equal to gamma after beta, so we can forget about alpha, and we get that R of A is the path algebra of the following quiver with no relations. So we have T1, T2, and T3, the arrow beta op from T3 to T2, and the arrow gamma op from T1 to T3. Note that R of A is hereditary, since we have no relations, and so it's quasi-hereditary for any order, in fact. Now let's try to compute the second RIngel dual. Let us write the algebra R of A in the following way. So we have the vertices 1, 3, and 2, an arrow from 1 to 3, and an arrow from 3 to 2. Note that we have the opposite order. Now 1 is the maximal element, 2 is the next one, and 3 is the minimal element. Just like in the previous case, this algebra has 6 indecomposable modules. The module L1 concentrated at the vertex 1, which coincides with its injective envelope I1, and with the costandard module nabla 1. Then we have the simple L2, which is concentrated at the vertex 2, which coincides with P2 and delta 2. We have L3, which is concentrated at the vertex 3, and since 3 is the minimal element, L3 coincides with delta 3, with nabla 3, and with T3. We have the injective module I3, which is concentrated at the vertices 1 and 3 with the identity between them. We have the projective module P3, which is concentrated at the vertices 3 and 2 with the identity between them, and it coincides with nabla 2 and with T2. And finally, we have the three-dimensional indecomposable module, which is concentrated at all vertices, and this module is P1, delta 1, I2, and T1 at the same time. So now the RIngel dual of the RIngel dual of A is the opposite of the endomorphism algebra of T1, T2, and T3. This is our T1, that's a three-dimensional indecomposable module, that's T2, it's P3, and this is T3, which is L3. Here we have a surjection from T2 onto T3, which we call Xi, and an injection of T2 into T1, which we call eta. There are no relations because we cannot compose eta and Xi. Now, if we take the opposite of the endomorphism algebra, we then will have three vertices, T1, T2, and T3, the arrow eta op from T1 to T2, and the arrow Xi op from T3 to T2. And we see that this coincides with the original quiver for the algebra A. Okay, some extra problems and questions at the end. Problem question 1. Let X and Y be two tilting modules over quasi-hereditary algebra A. Show that the dimension of the home space over A from X to Y is equal to the sum over all I from 1 to K, the multiplicity of delta I in X times the multiplicity of nabla I in Y. Problem question 2. Construct an example showing that the functor f is not exact on the whole category A mod in general. Problem question 3. Prove that G is exact on f delta over R of A with all details. Problem question 4. Prove that f induces an isomorphism between x1 over A from nabla I to X and x1 over R of A from delta I to f of X for any x in f of nabla over A with all details. Problem question 5. Compute the RIngel dual for the path algebra of the following quiver. We have the vertices 1 and 2 and two arrows from 1 to 2. Thank you very much and see you next time.